Diffuse interstellar bands are absorption features seen in the spectra of astronomical objects in the Milky Way and other galaxies. They are caused by the absorption of light by the interstellar medium. More than 400 bands have now been seen, in ultraviolet, visible and infrared wavelengths. The origin of DIBs was unknown and disputed for many years, and the DIBs were long believed to be due to polycyclic aromatic hydrocarbons and other large carbon-bearing molecules. However, no agreement of the bands could be found with laboratory measurements or with theoretical calculations until July 2015, when the group of John Mayer announced the unequivocal assignment of 2 lines for C60+, confirming a prediction made in 1987. Discovery and history. Much astronomical work relies on the study of spectra. The light from astronomical objects disperse using a prism or, more usually, a diffraction grating. A typical stellar spectrum will consist of a continuum, containing absorption lines, each of which is attributed to a particular atomic energy level transition in the atmosphere of the star. All astronomical objects are affected by extinction, the absorption of photons by the interstellar medium. Interstellar absorption predominantly affects the whole spectrum in a continuous way, rather than causing absorption lines. But in 1922 astronomer Mary Lee Hager first observed a number of line-like absorption features which seemed to be interstellar in origin. Their interstellar nature was shown by the fact that the strength of the observed absorption was roughly proportional to the extinction, and that in objects with widely differing radial velocities the absorption bands were not affected by Doppler shifting, implying that the absorption was not occurring in or around the object concerned. The name diffuse interstellar band, or DIB for short, was coined to reflect the fact that the absorption features are much broader than the normal absorption lines seen in stellar spectra. The first DIBs observed were those at wavelengths 578.0 and 579.7 nanometers. Other strong DIBs are seen at 628.4, 661.4 and 443.0 nanometers. The 443.0 nanometers DIB is particularly broad at about 1.2 nanometers across. Typical intrinsic stellar absorption features are 0.1 nanometers or less across. Later spectroscopic studies at higher spectral resolution and sensitivity revealed more and more DIBs. A catalogue of them in 1975 contained 25 known DIBs, and a decade later the number known had more than doubled. The first detection-limited survey was published by Peter Jenniskens and Xavier Desert in 1994, which led to the first conference on the diffuse interstellar bands at the University of Colorado in Boulder on May 16 to 19, 1994. Today over 300 have been detected. In recent years, very high-resolution spectrographs on the world's most powerful telescopes have been used to observe and analyze DIBs. Spectral resolutions of 0.005 nanometers are now routine using instruments at observatories such as the European Southern Observatory at Cerro Paranal, Chile, and the Anglo-Australian Observatory in Australia, and at these high resolutions, many DIBs are found to contain considerable substructure. The nature of the carrier. The great problem with DIBs, apparent from the earliest observations, was that their central wavelengths did not correspond with any known spectral lines of any ion or molecule, and so the material which was responsible for the absorption could not be identified. A large number of theories were advanced as the number of known DIBs grew, and determining the nature of the absorbing material became a crucial problem in astrophysics. One important observational result is that the strengths of most DIBs are not correlated with each other. This means that there must be many carriers, rather than one carrier responsible for all DIBs. Also significant is that the strength of DIBs is broadly correlated with the interstellar extinction. Extinction is caused by interstellar dust, however, DIBs are not likely to be caused by dust. The existence of substructure in DIBs supports the idea that they are caused by molecules. Substructure results from band head in the rotational band contour and from isotope substitution. In a molecule containing, say, 3 carbon atoms, some of the carbon will be in the form of the carbon-13 isotope, so that while most molecules will contain 3 carbon-12 atoms, some will contain 2 12C atoms and 1 13C atom. Much less will contain 1 12C and 2 13Cs, and a very small fraction will contain 3 13C molecules. Each of these forms of the molecule will create an absorption line at a slightly different rest wavelength. Polycyclic aromatic hydrocarbons, long carbon chain molecules such as polyene and fullerenes are all potentially important. Fullerene C60+ identified as carrier of 2 diffuse interstellar bands. After nearly 100 years since they were first observed, the Buckminster fullerene ion, C60+, was unequivocally assigned as the carrier of 2 diffuse interstellar bands. The paper by E.K. Campbell, Holtz, Gerlish and J.P. Mayer was published on August 16, 2015. The first prediction that C60+ was a carrier of DIBs was put forward by chemist Harry Kroto, co-discoverer of C60, and later with astronomer Mike Jura. Kroto wrote in 1988, "Starlight will ionize much of the interstellar C60 present, and so C60+ should be ubiquitously distributed in space, making it a viable candidate for the carrier." In 1987, Kroto also proposed that the present observations indicate that C60 might survive in the general medium, protected by its unique ability to survive processes so drastic that most, if not all, other known molecules are destroyed. The remarkable achievement in 2015 was the result of many years of painstaking work performed by the group of John Mayer at the University of Basel, developing state-of-the-art spectroscopic techniques to create conditions in the laboratory that simulated the extremely low temperature and low pressure of interstellar space. The critical experiment in the final phase leading up to the assignment was carried out by Mayer's group, which originally observed 2 lines of C60+ in a neon matrix at low temperature in 1993. Based on that result, B.H. Foing and P. N. Renfreund were able to detect 2 strong DIBs in close proximity to the 2 laboratory absorption lines. However, the matrix caused shifts in the laboratory reference spectrum, and therefore, an unequivocal assignment to DIBs could not be made at that time. Mayer spent the next 20 years developing the demanding state-of-the-art techniques to permit direct comparison of laboratory results to DIBs.